Hello everyone, thank you for coming. The topic of our talk is about achieving remote code execution on Nissan Leaf cars that can be used to control critical body elements of a vehicle from the internet. This is the agenda of our talk. We will start with the introduction of ourselves and the target. Then we will talk about how we've built a test bench and bypassed the anti-theft protection. After that, we proceed to Bluetooth internals and the vulnerabilities we have found there. The next chapter is persistence on a system with data exfiltration over the internet. And finally, we will cover vulnerabilities we have found in CAN communication that can be used to control critical body elements of a car. So let's begin with the introduction. Today we are representing our company, PCA Automotive, or PCA in short. We provide vulnerability research and penetration test services for various industries, including automotive. I'm Mikhail, a senior security researcher at PCA.
I'm Radu Motsman. I'm senior security researcher at PCA Automotive as well.
And also Polina, today with us, sitting in the front row. In 2023, we conducted a vulnerability research of a Nissan Leaf that was produced in 2020. As any modern vehicle, Nissan Leaf consists of gateway unit, which is used for CAN packets filtering based on predefined routing rules, a telematic unit, which is used for cellular communication, and infotainment system, EV in short, which provides various connectivity features such as Wi-Fi inclined mode only, USB, Bluetooth, Apple CarPlay and Android Auto applications, navigation via GPS, and maps. To build a test bench, some components were purchased from eBay. However, so-called component protection was enabled for these devices. This means that, for example, telematic unit and EV from different cars will not be communicating with each other due to this protection. So this is why we went to the closest Budapest auto junkyard to gather all the needed units, such as EV, gateway, body control module, instrument cluster, and others. Finally, we were able to build a nice-looking test bench for Nissan Leaf. The anti-theft protection is pretty common in modern vehicles. It's used to prevent the theft of a head unit itself or unauthorized access to the underlying systems. This includes locking functionality, which is implemented in the firmware. You can see an example of this on the slide. It shows system is locked, green, contact the dealer. Green error code will be explained later in this talk. This also includes VIN integration and reduction of functionality. Let's examine the implementation of the anti-theft protection in Nissan Leaf EV. When EV is powered on, a special anti-theft challenge must be solved beforehand. EV communicates with a designated ECU to solve this challenge. EV communicates with a designated ECU over the CAN bus. This is important to solve this challenge. If EV doesn't receive any response from the ECU, then it's considered as green error, as was shown on the previous slide. If incorrect response is received, then it's red error. If everything went successfully, the anti-theft challenge is considered as solved. In the table, you can see the communication messages between the devices to solve this challenge. Here we will describe the structure of these messages. As you can see, EV sends a function number, a seed value, a constant blob, and a checksum. ECU responds with the same function number, a calculation result, and a checksum as well. The checksum is calculated as the sum of all bytes in the message payload except the last 2 bytes. To bypass the anti-theft protection, we analyzed runtime CAN communication between EV and the anti-theft ECU. It revealed that the seed maximum value is 0x20, which allowed us to build a solution table with correct challenge response for every seed. We implemented a Python script that responds with the correct calculation result to EV, which basically bypasses the anti-theft protection. From now on, we can enable and boot any Nissan Leaf EV. Let's take a look at the Nissan Leaf EV from the hardware point of view. On the top of a metal cover, you can notice OM part number and FCC identifier. These numbers are useful if you want to purchase the same EV device with the same configuration as installed in your car. Under the hood of EV PCB, there are Renesas RH850 microcontroller designated for CAN communication, several Cypress SPI memory chips, and finally IMX6 processor manufactured by NXP. This is the main CPU of the board. On the other side of EVPCB, there is eMMC NAND chip with the main root file system, and surprisingly, Wi-Fi plus Bluetooth chip is located on the HMI PCB instead of EVPCB. This one is manufactured by Alps Alpine. After initial hardware and firmware analysis, the infotainment architecture looks like this. In the middle, we have IMX Quad, which consists of 4 Cortex-A9 cores. They're all running a Linux operating system, and it's also connected to Renesas RH850 and has a dedicated driver for this communication. RH850 is responsible for CAN communication with external units in both ways, input and output. We will share more details on it later in the talk. On the left, we have a persistent storage memory. This one is maintained by eMMC chip with a Linux root file system on it. And also we have SPI chips with boot images. In terms of connections, RH850 chip is connected to the gateway unit, and telematic unit is connected directly to IMX system. Finally, the external interfaces, such as Bluetooth, Wi-Fi, and USB. Wi-Fi and Bluetooth coexist on the same baseband chip manufactured by Alps Alpine. Well, now is the time to talk about Bluetooth internals and its implementation on Nissan Leaf EV. In general, Bluetooth consists of several protocol layers. The lower layer is handled by a baseband controller, and the next layer is named L2CAP, which is basically the transfer protocol in terms of Bluetooth technology. These two layers are glued together using HCI layer, which stands for Host Controller Interface. All upper layers are based on L2CAP and implement various functionality such as service discovery, audio-video transmission, and others. The Bluetooth stack used on Nissan Leaf EV is named as Blue Dragon Evolution Stack. This is a 32-bit ARM ELF executable launched with root permissions. The stack implementation is proprietary, which means that some other devices might be vulnerable to the attack we're about to explain as well. Additionally, Bluetooth logic is divided into multiple libraries, all linked into the ELF executable. PI and ISLR security mitigations are enabled, but stack canaries are disabled for all the Bluetooth libraries. Even though ISLR security protection is enabled, all the libraries, for some reason, are loaded at the fixed addresses, which makes the ISLR protection completely pointless. Pairing is essentially an authentication mechanism used to securely connect Bluetooth devices. There are two different approaches to pairing: legacy pairing and simple secure pairing, SSP in short. SSP is a modern authentication mechanism based on input-output capabilities of a device. It's based on profiles and procedures. Let's consider an example of pairing a headset to your mobile phone. In this case, headset has no input, no output profile because it doesn't have keyboard or display, while your mobile phone has keyboard display profile because it has both. Therefore, just works procedure is used for authentication. Legacy pairing is pin code based, which is equivalent to passkey entry in SSP. Nissan Leaf head unit accepts pairing requests only from the designated sub-menu shown on the slide. However, no user interaction is needed to pair an attacker's control device when this menu is opened. In that case, how can we force a user to open this menu? Well, in fact, it can be done by jamming the Bluetooth radio frequency. Let's say a user is listening to the music from the already paired mobile phone. In that case, jamming will cause noise, forcing a user to reconnect the device. And to do this, obviously, a user needs to open this menu, which allows us, as an attackers, to pair with the EV. Well, in Bluetooth, hands-free profile describes how to place and receive audio calls from a device. So let's give some definitions. Audio gateway is the device acting as a gateway of audio. It could be a mobile phone or an attacker's control device. Hands-free unit is a device acting as a remote audio input and output. It could be an infotainment system. Hands-free profile is a control channel that works on top of a RFCOM connection. It manages the communication process through signal control messages. AT command protocol is used for messages transmission. And finally, the audio stream itself is transmitted over another channel, which is out of scope for this talk, unfortunately. Here is an example of hands-free profile communication. When hands-free connection is established, hands-free starts the communication by notifying audio gateway about its supported features. Audio gateway responds with the supported features as well, and essentially they configure the transfer protocol for incoming audio stream. As you can notice, all the communication happens through AT commands, as I mentioned on the previous slide. Almost every AT command in hands-free profile is standardized. However, some implementations might use vendor-specific commands. They might be used for specific operating systems or voice assistants. As an example, you can see Apple AT commands in hands-free profile. The first one is used to obtain the current Siri information status, and the second one is to obtain the state of incoming audio from an iPhone. Now let's talk about the vulnerabilities we have found in hands-free profile. Little disclaimer, all the code shown in this talk is pseudocode and not the actual source code, all right? So the function responsible for parsing responses in hands-free profile is shown on the slide. Its name is hands-free parse response, indeed. The controlled incoming buffer is passed to this function. First of all, the function must determine what command has been received. We are interested in Android command response. Then it decides what operation is specified within the received data. It's a prop operation in our case. When the command and the operation are determined, the getParameters function is used to obtain the parameters of the received response. The parameter lengths for this operation are stored in prop length variable. Finally, if the number of the obtained parameters is 2, the first one is copied into the stack buffer. You can notice the out-of-bound validation right before the memCopy function. However, it validates only the lower bound of the parameter length. There is no upper bound validation within the function, which means that there is stack overflow vulnerability in params variable. Now recall that stack canaries are disabled for all the Bluetooth libraries, which means that we can take control of the execution flow. And a little bonus on top of that, consider two other operations for Android command response, audio source and VDS. They suffer from the same issue described before. Therefore, in hands-free parse response function, we have not one, but multiple stack-based buffer overflows. Incredible. Now that we have understood the vulnerability's root cause, it's time to delve into the exploitation strategy, and spoiler, it's quite trivial. Having a stack buffer overflow without stack canaries enabled, it's only natural to build a ROP chain to execute system function with a controlled payload. We have some restrictions on several bytes in a ROP chain payload, but they don't affect us much. Additionally, we've built such a ROP chain that the normal code execution flow continues gracefully. But the question might arise, where do we store system function payload? Well, to not increase the payload for graceful continuation and to bypass the restriction, we decided to utilize another Bluetooth profile named AV-CTP. It stands for Audio-Video Transmission Profile, and the communication in this profile happens in a fragmented way. This means that there is a global buffer used for fragmentation. And we know the address of this fragmentation message buffer because all the Bluetooth libraries are loaded at the fixed addresses. This is where we store our system function payload. Finally, let's discuss the content of the system function payload. It might look trivial, but we had some issues with it. And the main problem was the firewall. It was enabled on the system and is based on the IP tables rules. Some of these rules discard outbound connections except a few legitimate ones. As long as Bluetooth service is launched with root permissions, it means that we execute code as root in our ROP chain, right? So essentially we have enough permissions to modify the IP tables and remove the drop rules shown on the slide. In the end, the architecture of our exploit looks like this. First, we set up an access point. Then we push a one-click Bluetooth exploit, which modifies the firewall. and forces the path supplicant to connect to our access point. And finally, we launch a reverse shell on top of it over TCP/IP stack. By doing that, we were able to get a root reverse shell with 100% stability. At this moment, we have obtained one-click remote code execution on Eevee, 0.5 clicks if the jamming magic works on the end user, plus we have root permissions on the system with the ability to load custom kernel modules. This is important. Now let's talk about the system where we've obtained code execution. On the slide, you can see some information about the system. Pretty old U-boot is used as a bootloader coupled with the old Linux kernel 3.14 version. SEL Linux is disabled on the system, however, file system integrity control is implemented by DM Verity. Basically, for an attacker, it means that we can't modify arbitrary files to get persistence on the system. While poking around the system, we came across a situation where the debugging was needed. But we faced a problem when we tried to attach GDB to a target process of our interest. For some reason, system rebooted at the next breakpoint we've set. That seemed kind of strange. Perhaps the target process had signal handling logic, which is why SIGTRAP was cached and system rebooted. Apparently, that assumption was wrong. We haven't found anything related to this in the implementation of a target process. Probably it's a kernel's fault then. Maybe it intercepted specific signals, such as SIGTRAP, and forced system to reboot. Looks like we were right. You can see weird demask login messages while we were debugging a process on a system. There is something related to a custom kernel driver named XCHND. Remember the name of this kernel driver, as we will come back to it in a minute. At this point, we still haven't obtained a kernel image to begin our investigation. Yes, you can find the kernel image in a firmware, but it's obviously compressed. Trying to decompress the image, it became obvious that no standard compression algorithms worked on it. Binwalk also didn't reveal any meaningful results. This means that we need to explore the bootloader image to determine how it decompresses and loads the kernel. Before going further, it makes sense to look at the uimage header. You can see that uimage is an ARM Linux kernel, obviously. Even so, the compression value is unknown to us. We checked many uboot repositories online, but weren't able to find any matching value. So we took this value, OX4D, and searched the bootloader image to find where it's used. It turned out this value is used in bootm loadOS function, which is responsible for kernel image decompression and loading it at a specified memory location. OX4D compression type represents LZ77 compression. From the LZ77 decompress function parameters, you can notice that the decompressed image will be stored in the image buffer variable. At that time, we had no idea what this compression is, so let's figure it out. Apparently, LZ77 is a lossless data compression algorithm that was published in 1977. There are public repositories with its implementation, however, none of them worked for our kernel, unfortunately. As long as we have implementation of LZ77 decompression functionality in a bootloader image, we can just emulate it and get the decompressed kernel. Killing emulation framework was used for this purpose. After getting the decompressed kernel image, we could start searching it for that weird kernel driver. Turned out, XCHND basically stands for Exception Handler Driver, bingo. After a quick reverse engineering of its implementation, it revealed that the driver catch exceptions from processes using the registered kprobes and jprobes. After it caught an exception, the driver does predefined actions. In case of SIGTRAP, it's system reboot. Unfortunately, we can't just unload it from the system because it's built straight into the kernel image. So what can we do to stop it from functioning? The solution is dumb and straightforward. As it uses kprobes to catch signals, we can just unregister them from our own Linux kernel driver, because we have permissions to do that. Another solution is to call the driver exit function from our kernel module as well to disable it. In either way, the exception handler driver was disabled and we got the debugging capabilities on the system. At this point, we've understood the compression mechanism used for kernel image, uncompressed it using emulation, disabled the exception handler driver, and got the debugging capabilities on the system. I pass the microphone to Radu, and he will explain further exploitation steps we took in this research.
So at this moment, we have code execution with root access on Eevee, but after reboot, it will be lost. So it's time to fix it by achieving persistent code execution. In our research, we tried the following techniques. Logic issues while processing configuration files from writable eMMC partitions, and compromising secure boot chain. So we started with the first one. Surfing around the configuration files, we noticed the ALD service, authorization level daemon. It allows to disable security configurations, for example, enabling SSH server and disabling the firewall. In the SSH service configuration file, it checks the existence of SSH enabled file in a writable partition. In case of existence, SSH server will be started. As a result, the following bash commands can be used to gain SSH access over the network after system reboot. But on the newer Eevee version, a new dependency to SSHD service was added to tie SSH checker service. It starts before the main one. If the current ALD level is lower than the required level, then the SSH enabled file will be deleted and SSH disabled file will be touched. And unfortunately, this is our case. But we can create a symbolic link with the name SSH disabled file, which points to the SSH enabled file. So when TTI SSH checker service will try to touch SSH disabled file, it will also create SSH enabled file. As a result, SSH server will be started. Enabled SSH server on every system reboot is very useful for security research. But if a car drives away, we lose network connection and can't execute code. So we switch to the secure boot. IMX processor uses hub high assurance boot for this purpose. For Eevee system, the secure boot process looks like this. Hub starts from boot ROM and loads the next stage bootloader plus CSF common sequence file from SPI. Inside, CSF contains signature and certificates. After loading, hub authenticates them. That bootloader then loads the DTB, device tree block, and its CSF, along with the Linux kernel uimage plus its CSF from eMMC. Hub authenticates this as well. Linux uses boot arguments from the DTB as a kernel command line. Finally, the DMVerity subsystem used to mount root file system. It takes parameter from the Linux kernel command line. During the boot process, hub is loaded at the 0 address. Even after the Linux starts, the hub code still exists in the memory, likely because each boot stage needs it for authentication. From Linux, we can read this memory via accessing physical memory. By reading the specific memory range, we were able to dump the hub code. After analyzing the dumped code for hub, it was identified that it is vulnerable to the known bug. It is a Stack Overflow vulnerability while processing CSF certificate. In the exploitation, we force hub to load arbitrary CSF to accept any CSF signatures. So we can compromise secure boot from the beginning, but that exploitation will take a lot of effort. There is an easy way. We can force the system to load arbitrary DTB. As the payload, we patched the boot args inside DTB and added a new parameter for DMVerity, ignore corruption. This parameter forces the system to skip any possible errors during hashes validation. After the rebooting, we can modify the file system and put our code into the bash script, which runs on every system boot. To have a stable connection when a car drives away, we also need to have the ability for data exfiltration. Like in every modern cars, Eevee has internet connection through telematic unit. After the test, we noticed that DNS requests to the attacker servers are not filtered, so we use DNS-Cat2 to set up a tunnel over the internet to our TCP server, which hosted on EV. To sum up, at this moment, our code will be started on every EV boot, and it can be controlled through internet. The next task for us is moving to the other ECUs. In automotive environment, ECUs are typically connected via CAN bus, so we need to find a way how to gain CAN bus access from EV. From hardware record, we identified that EV is connected to the CAN bus through RH processor. Additionally, RH is connected to IMX through over SPI bus. There are several ways how to gain CAN bus access. We can use legit interfaces and API, which are used by EV. We can modify the firmware of RH, or we can just exploit vulnerabilities on the RH side. So at first, we tried to understand how EV legitimately communicates with CAN bus. Inside EV, there is a package manager. So on the file system, there are descriptions for all installed packages. Just by grabbing CAN word, we found potential servers. While looking at its dependency, we found that it communicates over ENC SCC network interface. But the traffic of it looks pretty unusual for network interface. After searching information in the internet about this network interface, we have found that it is based on the ENC subsystem. This subsystem provides handy interface for communication between devices. It is defined in the SDK, which can be downloaded from Bosch website. Also, some description information can be found in the push request. Plus, on the EV system, we found binaries, which can help us to test ENC interface. After summarizing all the get-read information, the architecture of ENC subsystem is shown on the diagram. This subsystem enables point-to-point communication between two devices over SPI hardware. Clients communicate with the ENC network device driver, which passes requests to the SSI32 block device driver, which finally communicates with the SPI bus. On the slide, you can see a typical client for the ENC interface. It largely looks like standard socket-based code. Important note here is the value of ports. All known ports for ENC interface can be found in the SDK. Each port is used to access specific service on the other device. Most of the port names are pretty self-explanatory. Let's go back to the CAN bus access. On EV side, CSM service is responsible for sending messages over RH to the CAN bus. It uses two entities. Signal, for one-time CAN message, it is used to notify ECU clients or subscribe for events to other ECUs, and request. This one contains multiple CAN messages with connection phase. CSM service sends requests over the ENC interface to the ports shown on the slide. On the screen, you can see how these requests transferred to the CAN messages. ENC request contains two fields, bus type and internal address. These values are used to identify suitable entry in the global array inside RH firmware. Later, we will say how we got RH firmware. In turn, this entry contains the CAN ID for the message to be sent from RH to CAN bus. Let's summarize. Basically, we can use a legit interface to communicate, to send CAN messages. And it seems that payload of a message can be controlled. But unfortunately, we can't send messages with arbitrary CAN ID. We can only use CAN ID, which are defined in the RH firmware. So the next attempt was to compromise the RH firmware. For that, it will be useful to understand update process. Basically, the code of IMX can update the firmware of RH using specific executable and update file on the file system. The update file has the DNL binary format. It's a proprietary format. We dissected it by reversing the update utility. For the update process, it uses ENC interface with the download port. UDS requests and response go on top of ENC interface. The update workflow via UDS common is pretty common. Important step here is the signature transfer. This signature is used for validation of the uploaded firmware while processing the end transfer UDS common. During the boot, firmware is validated in the similar way. So inside RH firmware, we identify security mechanism which protects against firmware modification. But we gain the firmware file of RH and can analyze it for vulnerabilities. As I mentioned earlier, the INC interface has many ports. Each port is linked to a service on the RH side. Inside the firmware, there is a global array that holds handlers for each service. Because of this, attack surface for RH is quite large. Important to note, since there is no debugging mechanism, any tracing functionality can be useful. Inside the RH firmware, there are many calls to trace execution. In fact, this trace information is sent over the INC interface through the DLT port. By accurately dissecting the traffic like on the screen, we can understand what was executed on the RH side. During the research, we found a vulnerability in the service net broadcast. Its request processed in the following callbacks. The first one just checks the size of input data. The second one places the data in the global memory. And finally, the third one performs the real job and parses input data. Without going too deep into the handler, we found the following code. This code contains the loop which copies data. However, this loop is only limited by the size of the packet. Destination for copy operation is a buffer located on the stack. Since the packet can be larger than the local stack buffer, this can lead to stack overflow, overwriting data beyond the buffer. In our case, it overrides the saved LP register, which serves as the return address in the RH architecture. On the RH side, exploitation of this vulnerability is pretty easy. We don't have any limitations for payload. No exploit modifications were found in the firmware, such as stack canaries. Moreover, global memory is RVX. As preliminary, we just put shell code in the global memory using the LTA request. So by overwriting the return address with the address of shell code execution can be achieved. But on IMX side, we have issues to run our exploit. Only one client can open socket for net broadcast port. CSM service constantly communicates over it. If the service is killed, then watchdog will be triggered and EV will be rebooted. To fix the problem, we inject our exploit code into the service. For that, we disabled signal handlers in the kernel, as discussed previously. With code execution on RH side, we can send arbitrary CAN messages. EV is connected to several CAN buses. One of them goes to the gateway. In general, this ECU is used to pass or filter CAN messages from one CAN bus to other according internal rules. To test these rules, we just brute all CAN ID and observe on which buses our message will be visible. We notice that CAN messages with diagnostic ID can be passed from EV to such critical buses as vehicle, ADAS, and chassis. The next challenge for us was to find diagnostic UDS commons, which can control critical car elements. For that, we decided to buy a special tool set named Console 3. It consists of hardware and software elements. The main point is to capture transmitted UDS commands from the device to a car and replace them in our exploit. This is a user interface for Console 3 application. It supports communication with various ECUs like BCM, ADAS, and chassis, and can control such elements like doors, wipers, horn, and others. Console 3 transmits UDS commands to a car over the USB bus. We can capture the communication traffic and see UDS commands here. An example of how it looks in Wireshark is shown on the slide. So we were able to obtain the following list of interested UDS commands supported by Nissan Leaf. This includes commands to manipulate mirrors, doors, steering wheel, and others. Having the code execution on RH, we can control all these elements of a car. The video demonstration of them will be provided in a minute. Let's summarize everything we have covered in the talk. So we have initial state of our system as we described in the beginning of the talk. We start our attack chain by launching a one-click Bluetooth exploit to get privileged code execution within the Linux system. After that, we gain persistence on the system by exploiting the NDA vulnerability in the IMX hub. This allowed us to modify the root file system, injecting a special code that is launched on every system boot with root permissions. Once persistence is achieved, we utilize the telematic unit to connect to our backend server for data exfiltration. From this moment, we gain access to the EV through the internet on every system reboot. Finally, we exploit the vulnerability in the RH to be able to send raw CAN messages from the EV. Gateway doesn't restrict us from sending CAN messages dedicated to body control unit and others. Essentially, this means we can manipulate critical body elements of a vehicle from the internet. Here is the video demonstration of the attack chain with the real car we had in our lab. We developed a server and user interface for remote vehicle control. Please remember, all of this was done for demonstration purpose only.
And start.
Alright. I'm starting monitoring now. Tracking started. Okay, GPS tracking is working.
Okay, perfect.
I am starting the phase now.
Okay. We got the deface. Thank you.
I am stopping the phase now.
Deface stopped.
Alright.
Let's try to record audio.
Okay. Starting audio recording.
Hey, this is PC Automotive, and we are testing audio recording in Nissan Leaf.
Alright. Audio recording stop. I started downloading. Audio recording downloaded. I play it in the browser now.
This is PC Automotive, and we are testing audio recording in Nissan Leaf.
I play audio in the car.
This is PC Automotive, and we are testing audio recording in Nissan Leaf. Thank you. Let's try to do screenshot now.
Alright. I'm starting screenshot now. Okay, we received screenshot.
Right. Next, body controls.
Alright. Can I send horn control? Okay, I send that. I am sending mirror commands now. Alright. Okay, I'm sending Viper now. Okay, steering started. Steering wheel, send.
Okay. Vipers. And the steering wheel.
Okay, steering.
Got the steering wheel. Okay, thanks.
The list of the identified vulnerabilities is shown on the slide. Almost all of them were used in the demonstrated attack chain, except the second. This one can be used for mid attack during EV connection to backend. This can be achieved because EV incorrectly verified service certificate. Regarding the disclosure process, we communicate with all possible actors. We disclosed our findings to Bosch and Nissan. They created a patch for vulnerabilities and agreed to publish these materials. As a result, SRG registered CVE numbers for us. They will publish soon. Finally, we would like to thank all members of security research team which contributed to this research. Thank you guys for your attention. If you have any question, don't hesitate to ask them.
Yep. Yep, Nissan Leaf. They identified vulnerabilities, how do I put it? Only specific to this vehicle, most of them, but some of them might be in some other components of other like Nissan cars. Probably, we can't say that for sure because we didn't validate that. So yeah, the possibility of it is like maybe. Thanks. Any question? No, that's exactly the point, because gateway passed through the UDS commands, and that's the actual vulnerability, because in a normal like execution, that shouldn't happen. So yeah, yeah, exactly.
Just to follow up to the other question. So at the very end, you said you had to talk to Bosch, right? So some of the components are Bosch component, not Nissan component, right? And they could be found in other cars as well, or not?
EV component is developed by Bosch. So in that case, we started our communication with Nissan. But after that, we started communication with Bosch because originally it comes from them.
Yeah, because it's a tier one provider.
Yeah.
So in your experience, what is the best way to actually track down all the vehicles that actually could potentially be impacted by a component that belongs to a tier one provider?
That's a tough question, because it's not only related to, for example, ECU itself, but some other software that might be used in other ECUs not related to Bosch or some other vendor. So at that point, we don't have an answer to that, unfortunately. So we don't know, except if you purchase the devices like ECU you're interested in and check it more manually. So that's the only way.
Because the CVE will only mention the specific software version or even component, but it will not. Is there on the Bosch side some link towards all the cars that actually include that version? Is there a way to figure that out? Like, it's a basic supply chain management problem, right? So, but it's a critical one, especially when we think about cars and the ridiculous software errors that they have and the amount of errors that they have.
Exactly. We don't know the answer to that. So it's better to ask Bosch if they can provide such an information, but we can't be sure that it's possible.
Yeah, I'm not blaming Bosch in particular. I'm pretty sure all the other tier ones are as bad as that. So,
yeah. Okay, thank you. Right. All right, guys, if you don't have any question or you have one but don't want to ask them right now, you can find us somewhere here in the event, and at our booth is it's still open, but I don't know, it's 4 p.m., so I don't know if it's open or not. So yeah, thank you.